Euclid's Elements, Book 3, Proposition 14. In a circle, two equal lines are equally distant from the center. And conversely, if two lines are equally distant from the center, then they are equal to one another. So let's have a circle. And we're saying that if we have in this circle, if we have two lines that are equal to each other. So let's have AB being equal to another line, CD. So here's our given. In a circle, we have two lines equal to each other, AB equals CD. From this, we can prove that they are equally distant from the center. And the second thing we can prove is if we start by knowing that they're equally distant from the center, so if we switch the givens, if we take it as a given that they are equally distant from the center, then we can prove that the lines are equal to each other, namely AB will equal CD. And Euclid defines in definition 4 the distance from the center as the distance of the perpendicular from the center to the line. So the first thing we're going to do then is we're going to find the center of this circle, let it be E, and we're going to, from this point, we're going to draw a line perpendicular to each of these lines. We know we can do this because from any point we can draw a line perpendicular to a given line. So from point E, we're going to draw a line perpendicular to AB, and from here we're going to draw a line perpendicular to CD. So we now have, let's have EF and EG. So we have drawn EF perpendicular to AB, and we have drawn EG perpendicular to CD. And we know from, is it prop 3.2 that, I think it is prop 3.2. Anyway, when a line goes when a line through the center touches another line, intersects another line not through the center, then it does, and it does it at right angles. So if this encounters this line at right angles, then it bisects it. So from this we know that AF is equal to FB. Likewise, we know that this is a line not through the center touching a line. There's a line through the center touching another line not through the center at right angles. Therefore, this is also bisected. And so we know that CG is equal to GD. But remember, we know AB is equal to CD. And AF is just, AF is half of AB, and CG is half of CD. And halves of equal things are themselves equal. Therefore, AF is equal to CG. So I'll change these out. Since these are all equal, I'm just going to make them, all these hash marks, equal. So this is equal to this. Now let's connect some more points. Let's connect EA and EC. And what we can see is we formed two right triangles. We also know that EA and EC are equal because they are radii of the same circle. So now what we want to prove is we want to prove that this perpendicular is equal to this perpendicular. Because if they are, then according to definition 4, the lines are equally distant. If this perpendicular is the same as this perpendicular, then the lines are equally distant from the center by definition. So we just want to be able to prove this. Well, how can we do that? Well, we have a right triangle. So we can use Book 1, Prop 47, the Pythagorean theorem. The Pythagorean theorem tells us that the square on this leg plus the square on this leg equals the square on the hypotenuse. And it's true for this as well. So we'll say that the square on FE squared plus FA squared, is equal to the square on the hypotenuse, EA squared. And this is also true for this triangle here. So we know that the square on GE squared plus GC squared is equal to the square on the hypotenuse, EC squared. But we already know that EA and EC are equal to each other. Therefore, their squares are equal to each other. Therefore, these two things equal the same thing are equal to each other. And in these two equalities, we already know that FA is equal to GC. Therefore, the square on FA is equal to the square on GC. So we can remove both of those, and the remainders will be equal. And so what we have here is that the square on FE, the remainder, is equal to the square on GE, the remainder. Well, we can just unsquare these, and we know that FE equals GE. And that's the third thing that we're trying to prove. That's the thing we're trying to prove. And that proves this first part, that if these lines are equal, then the perpendiculars from the center are equal, and therefore they are equally distant, according to definition 4. Now we're just going to switch our givens and prove the opposite. So now we're going to say, okay, given that these perpendiculars are equal, can we prove that AB and CD are equal to each other? Well, we can. Again, we're going to use a very similar kind of proof. It's with the same construction. Okay, we already know that these radii are equal. We know that these legs of these triangles are equal. And now we just have to prove, if we can, that FA is equal to FG. And then since this whole line is double that, if we can show these are equal, then their doubles are equal, and therefore so those are equal. So we're going to use the exact same thing. We're going to use Prop 47 again. And we know on a right triangle that the square on the legs is equal to the square on the hypotenuse. Therefore, FE squared plus FA squared is equal to EA squared. And likewise over here, we know that EG squared plus GC squared is equal to EC squared. And since we know these are equal, their squares are equal, so these two are equal. Therefore, these are equal. And in them, we know that the square on FE is equal to the square on EG because FE and EG are equal. Therefore, when we remove those, therefore the remainders are equal. Therefore, the square on FA is equal to the square on GC, which means we can unsquare them, and FA is equal to GC. So this is equal to this. But remember, FA is half, so if we double FA, we get, so 2 times FA is going to be equal to 2 times GC, but 2 times FA is equal to AB, and 2 times GC is equal to CD. Therefore, AB is equal to CD, which is the second thing we're meant to prove. Therefore, equal lines in a circle are equally distant from the center, or if they're equally distant from the 2 lines are equally distant from the center, then they are equal to each other. Since we have proved that, we conclude QED.